Hello there. We are now in section 2.7 where we're going to get introduced to a three-dimensional coordinate system that is different from our regular Cartesian or rectangular system. So one of them is going to be very similar to the polar coordinates that we saw in 2 dimensions, and then the other one is going to be completely different, but it's going to be talking about spherical coordinates in 3 dimensions. All right, let's get to it. In this first video, we will be looking at an introduction to cylindrical coordinates. So the overall objectives for the whole chapter talks about going back and forth from cylindrical coordinates to rectangular and spherical coordinates to rectangular. And of course, there's going to be a bridge between cylindrical and spherical coordinates, but we'll worry about that in the next video in the second half of this section. So for now, our focus would be spherical coordinates. So let's define spherical coordinates. The definition for spherical coordinate system will be a point represented by a new triple, r, theta, and z. Well, it's not exactly new because r and theta are essentially going to be the same r and theta from polar coordinates that we've already seen. Now, since we're living in 3 dimensions and we're trying to express things in third dimension, we have the z value. But the nice thing about this coordinate system is that the z value is simply going to be the z value. So really, this is pretty much polar coordinate realm, except we have a third component in z. So if we just look at the 2-dimensional version of what we're talking about here, we can take a look at the x and y space, or the plane to be more specific, and then we have a value here that we would call whatever x and y in Cartesian coordinates. So we have an x value and a y value, and then that translates into polar coordinates by having an r value, or radial distance, and having an angle theta. Now imagine a third axis that's coming right at you, and then now you have this picture, and you see this triangle here is exactly the same triangle that we would have had for Cartesian coordinates, or for polar coordinates, but now we have our third dimension. Okay, so the conversions you would see is exactly the same. These two equations and these two equations come directly from our polar coordinate transformations, and then now you just have z is equal to z, which is just the same z value. So that's why they didn't even bother changing that variable. Alright, let's take a look at some examples. Here we have rectangular coordinates given to you as, or find the rectangular coordinates if you have a given polar coordinates. So we have an r, a theta, and a z. Well, the only thing we need to do is figure out what r and theta are. So if we have r is equal to 3 and theta is equal to pi over 3, then our x is going to be equal to r times cosine of theta. So this will give us 3 times cosine pi over 3. Cosine pi over 3 is going to be 1/2. So this is 3 over 2. Y will be equal to 3 sine theta, or sine pi over 3. And this is going to be 3 root 3 over 2. And then our z component will be just 5. So the final result is that your rectangular coordinates representation of this point will be 3/2, 3 root 3 over 2, and 5. Okay. All right. Our next problem, they want us to find the cylindrical coordinates for this. So this we have to go backwards, and in order to do that, we'll use these set of equations. We have an x, a y, and a z, so z is still going to equal a 5, but now we have 1 and 1. So we can represent your r squared is equal to 1 squared plus 1 squared by this first equation. So we're going to get r equals square root of 2. And then our theta will be dependent on this equation where the tan of theta is equal to y, that's 1, over x, which is also 1. So this is 45 degrees, or let's call it pi over 4. So that would be our theta. Now, technically, this is going to be pi over 4, and we can also go around in a circle and call it 8 pi, 9 pi over 4, and etc. But let's just keep it simple. And then our z is just equal to 5. So our cylindrical coordinates will be r, an r value of root 2, theta value of pi over 4, and then z, a z value of 3. I'm sorry, a z value of 5. All right. Okay, so now let's do a few more problems. Here are a couple of problems where they ask us to write these equations in rectangular coordinates and try to identify the surface. We will continue to use our transformation that looks like this. So we want to make sure that we involve some sort of x, y's, and z's in it. So for this first one, you see that r squared times cosine squared theta is the same as r cosine theta quantity squared. So that's just x. So I would transform this by saying z is equal to r cosine theta quantity squared, which is equal to x squared. So z is equal to x squared. If you remember, when you have a surface with only two variables and a missing third one, it would be a cylinder. And remember what cylinders are, they're just starting off with a curve in 2 dimensions. In this case, on the xz plane, I would have a parabola. This looks like a parabola, and then the y is missing, so we're going to sweep that parabola along the y-axis. So in this case, it's a cylinder in the shape of a parabola, so I think we call that a parabolic cylinder. Okay. All right, let's take a look at the next one. We have r squared plus z squared is equal to 5. So for this one, I think what we want to do is we want to set r squared into x squared plus y squared. I believe we have that here. So let's write x squared plus y squared, this is r squared, plus z squared is equal to 5. So I think we know what that one is. If we take out the parentheses, this is simply a sphere of radius square root of 5. Sphere radius root 5. Centered at the origin if we want to be technical. Alright, let's take a look at the last one. The last one is cosecant. So I think it's hard to deal with cosecants and secants and stuff like that, so it's better if we're dealing with sines and cosines. So if we remember, I think cosecant is 1 over sine theta, And let's bring that over to the other side. So that'll be r times sine theta is equal to 1. And r equals sine theta. R equals sine theta. R times sine theta is y. So that's just y equals 1. So now this is a plane that's parallel to one of the coordinates planes. It's when we first started talking about 3 dimensions, we said the coordinate planes were like one of the variables equal to 0, and when one of the variables is a constant, then it's parallel to one of the planes. So if you attempt to draw this, I think it's manageable. This is your x, your y, and your z. You go to where y is equal to 1, and then you would draw a plane passing through that point y is equal to 1. Alright, so I think those are some of the examples that you might run into. And the main thing to know about cylindrical coordinates is that it is simply a 3-dimensional representation of polar coordinates. Okay, I hope that helps.